Welcome to Chemistry Online. Today we're going to talk about the autoprotolysis or the autoionization of water. Now we've previously talked about water and the fact that it is a polar molecule. It's polar by virtue of the fact that the oxygen and the hydrogens have different electronegativities. They have dipoles down the covalent bonds, and these combine to give a molecular dipole where we have one end of the molecule positive and the other end negative. If we look at the electrostatic potential map, it looks like this. The positive ends are focused here by the hydrogens, the negative, of course, up here by the oxygen. Now we talked about the fact that water was able to stabilize ions in solution. Well, water also interacts with itself by a mechanism called hydrogen bonding. If we take one water molecule and we place another one next to it, the oxygen end is going to line up with one of the hydrogens, and we're going to form what's known as a hydrogen bond. Now, a hydrogen bond is fairly weak. It's about 5% the strength of a covalent bond, but if you get a lot of them, it really does make a difference. And with water, we can get a lot. If we take another water molecule and place it next to it on this side, we can form two hydrogen bonds. Doing the same thing up top. Put another water up here. Quite obviously, we can extend this process forever, indefinitely. Water forms extensive networks of hydrogen bonding. This is a molecular model showing a water molecule in the middle surrounded by four additional, and these are hydrogen bonds. We can actually solve for a structure, for a cluster of water, and this is a rendering of that solution. And what I'd like to point out here is exactly how much interaction there is between oxygens, hydrogens, and adjacent oxygens. And these are all due to the hydrogen bonding. Lots and lots of interactions. Now, this structure is very, very dynamic. It changes, roughly 10 to the 6 times per second. So this is a snapshot in time, but the point is we have extensive hydrogen bonding in water. Well, there's one other thing that happens when we have hydrogen bonding. Here we have two water molecules adjacent to each other, and we have a hydrogen bond. If we take and put just a tiny bit of energy into the system, we can actually transfer this hydrogen without electrons, so it goes as a proton, from one water molecule to the other. When we do this, we form a hydronium ion and a hydroxide anion. Now, these can be handed back, same process, and we're back to having two waters. This process goes on very, very rapidly in water and goes on constantly. What we do is we form hydronium and hydroxide at a very low concentration. At 25 degrees in pure water, the concentrations of hydronium and hydroxide are both about 10 to the minus 7 molar. Now, the reason that water is able to do this is just like the same reason that water is able to stabilize other ions, except maybe even more effectively here. This is the hydronium ion, and this is its electrostatic potential map. You see this has a huge blue bottom on the thing. It's very, very, very highly charged. What I want to do is take a hydronium ion, and I'm going to place it in a cluster of 8 adjacent water molecules. Now our hydronium is here, and remember, it's our big blue ball. We're going to solve an electrostatic potential map for the entire cluster here, and when we do that, watch our big blue ball here. We wind up with a solution that looks like this. This is where our hydronium used to be. And you'll note that it's not only big and blue anymore, but it actually has a red peak on it. The ability of water to stabilize and disperse charge is just amazing, and that's the thing that makes water such a unique solvent. Well, if we have hydronium and hydroxide in pure water, then pure water, neutral water, actually consists of very low concentrations of hydronium and hydroxide, is constantly being formed, and is constantly converting back. When we have a process like this, where we have a forward and reverse reaction occurring simultaneously, we call this an equilibrium. And we show this with a set of double arrows like this. And what this means is that the reaction goes in the forward direction and the reverse direction simultaneously. Once the rate of change of the concentrations here reaches a constant, and that's very quickly in water, we say the system is at equilibrium.